Question number 26 is a gas law question. It gives you three different gases: argon, neon, and helium. And remember that when you talk about, notice that for the argon one here, they do give you the pressure in atmospheres. And remember that the pressure of a gas is directly related to the number of moles, which again is really the number of molecules or particles of the gas, times the gas constant times the temperature divided by the volume. So we know the temperatures are the same, so that's basically out. The volumes are all 1 liters, that's out, and R is always out. Now when I say out, I mean it's the same for all three gases. So the temperature, the R value, and the volume are the same, so the only thing that changes is the number of particles. So even though they don't tell you the pressure of the other gases, you can use this relationship here to know what the pressure of the other gases are. Because again, pressure is only dependent on the number of particles, the moles, times R times T over V. And when everything else is the same, the pressure is only directly related to the number of molecules. Okay, so if there's 4 here, and the pressure's 2 atmospheres, and here there's 2 particles instead of 4, well then we know that that pressure is 1 atmosphere. And you literally have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if there's 12 particles of helium, 12 atoms of helium, then that's going to have a pressure of 6 atmospheres. Okay, and they also tell you that you've got a ratio of 2 to 1 to 6 there. So that means the pressures are 2 to 1 to 6 in terms of pressure. So now we also know that if you combine all those gases together, so take the argon, take the neon, take the helium, and combine them all into the same 1 liter container, we know that the pressure total would equal the pressure of argon plus the pressure of neon. This is the Dalton's law of partial pressures plus the pressure of helium. And you put those three together and you would get a total pressure equal to 9 atmospheres. Okay, again, that's in a 1 liter container. So if you take those 3 gases and all put them, let's say, into the helium container, well, now your pressure is going to be 9 atmospheres. Okay, but now we're going to take all of those particles and we're going to put them into a 2 liter container, which means now your volume has doubled. So instead of a 1 liter container, now you've got more space. You've got more space for the gas particles to move around. The pressure, now this basically turns into a Boyle's law question, P1V1 equals P2V2, where if the volume doubles, the pressure has to go down by half. So if it was 9 atmospheres in a 2 liter container, it's now 4.5 atmospheres, which is B. Question number 27. Whoa. Question number 27 talks about a solution that is dissolving. So in this case, in step 1, here is the solute, and in order for the solute to dissolve or to dissociate in the water, it has to break apart. Okay, that process is always a positive delta H. Step number 2, the water or the solvent particle also has to move apart from itself. That is always a positive delta H. Okay, but now we're going to form some new interactions between the solute and the solvent, and that process here of making these new interactions is always a negative delta H. Okay, so the first 2 steps are always endothermic. The third step is always exothermic. Now, whether the overall process is exothermic or endothermic depends on how big those values are. If this releases a lot of energy and these don't require very much, then overall it's going to be exothermic. The opposite is also true. Okay, so the correct answer is D. Okay, question number 28. The key being here is that you have excess NaCl, which means no matter what, when you get done, you're going to have some sodium ions and some chloride ions floating around. That's a big, big way to solve this problem, is when you have something that's excess, it means there's going to be some of that left over. So notice in answer A, there is no chlorine left over. So A is out. In answer B, there's no sodium left over. So B is out. In C, you've got some sodium and some chlorine. In D, you've got some sodium and some chlorine. So at least C and D are possibilities. There's another 50-50 here. Okay. Now, what else do we have here is that if NaCl is an excess, then we know that the silver nitrate therefore must be limiting. And if AgNO3 is the limiting reactant, then there cannot be any silver left over. Now we're going to have nitrate left over because no matter what, we know that all nitrates are soluble. So everything has to have nitrates, which again, C and D both have. The only difference between C and D is that D still has that silver floating around there. Okay, and again, if that's the limiting reactant, that can't be there. The limiting reactant gets used up completely. All of that silver needs to be here at the bottom in the form of AgCl because that's the limiting reactant. Okay, so the correct answer is C. Okay, 29 through 33 refer to the following information. Again, we're back to gases. We've got the total pressure, PCl5. Then it's going to dissociate in an equilibrium system to make PCl3 and Cl2. Okay, so 29 says, which of the following is the most likely cause for the increase in pressure observed in the container as the reaction reaches equilibrium? Okay, remember that pressure is equal to, we just talked about this, nRT over V. So again, the volume hasn't changed, the temperature doesn't, the temperature's held constant, the volume of the container is the same, so the only thing that affects the pressure is the number of particles in that solution or in that mixture. So you're going from one gas particle, and as that breaks apart, it makes two. So if the number of particles in the container increase while everything else remains constant, then we know that the pressure has to go up. Okay, so let's see if we can find an answer that again refers to the moles or the number of particles increasing. Okay, A is talking about a decrease in the intermolecular attractions, no. Strength of intermolecular attractions, no. C, an increase in the number of molecules, which increases the frequency of collisions with the walls of the container, yes. Okay, C is the correct answer. An increase in speed, again, speed depends on temperature and molar mass. You're not going to see a significant change in the speed of the molecules. Question number 30. As the reaction progresses towards equilibrium, the rate of the forward reaction, so it says a pure sample of PCl5 is placed into a rigid container. Okay, so you're not starting with any PCl3 or any Cl2. So as the reaction first starts, it's going to start out really quickly, but then as it approaches equilibrium, it's going to start to slow down. Okay, it's not going to go to zero, because then again, remember, equilibrium is they're going at the same rate in opposite directions. Okay, so the forward reaction isn't going to increase. Okay, it is going to start out quickly, but then it is going to slow down. So as it progresses towards equilibrium, the forward reaction is going to decrease. Okay, but it's not going to become zero. Okay, it's going to keep going, so it's going to decrease to become a constant non-zero rate. So the correct answer is C. Okay, if the decomposition were to go to completion, which means if it goes to completion, that means it's not equilibrium. Okay, it says the total pressure in the container would be equal to what? Okay, well now instead of one gas particle, now you would have two gas particles. So in terms of overall what would happen in that container, again, the temperature isn't going to change. The volume isn't going to change, so your number of particles, again, P equals nRT over V. If your number of particles doubles and everything else stays the same, if this goes from one particle to two particles, that's going to double, and then therefore your pressure must also double. So the correct answer is B. Question number 32. Which of the following statements about Kp, the equilibrium constant for the reaction, is correct? Okay, so let's go back here and take a look. We know that the total pressure inside that container now is 1.4. So this is one of those cases where we can take our equilibrium constant, and we can, or our equilibrium scenario, and go, okay, the initial pressure of PCl5 is 1, and the total pressure inside that container now is 1.4. So if we think about the PCl5 in equilibrium with PCl3 and Cl2, and we make an ice table here, and this is whenever they give you the total pressure, this is a good thing to do. So initial change equilibrium. Again, the initial for PCl5 was 1. This is going to be 0. This is going to be 0 because initially there isn't any PCl3 or Cl2. This is going to go down by x. Those are both going to go up by x, 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 1 minus x. Okay, now, again, we could set this up with an equilibrium constant expression. The problem is we don't know the equilibrium constant, but we do know, again, up here, that the total pressure is the sum of those. So we can say 1.40 is going to equal 1 minus x plus x plus x. So taking all of those and combining them together gives you the total pressure. So that negative x, that positive x cancel each other out. Subtract the 1, x equals 0.40. So that means that at equilibrium, this value is 0.4, this value is 0.4, and this value is 1 minus 0.4, which is 0.6. So we're going to have 0.40 squared over 0.60. Okay? So let's see, what are our choices here? Whoa, went a little too far there. All they want to know, is it greater than 1, less than 1, equal to 1, or you can't figure it out? Well, I know that 0.4 squared is 0.16 over 0.60, and at that point I don't care what the answer is. I know that number is less than 1, so the correct answer to number 32 has to be B. Okay, number 33, some additional chlorine is injected into the system at equilibrium. So chlorine is a product. So when you add a product, we know that the reaction is going to shift to the left, which means the amount of chlorine that you added is going to go down a little bit, but it's going to stay still higher than where you started at. Okay, so which of the following graphs best shows the rate of the reverse reaction as a function of time? So again, that goes up really, really quickly. Then it's going to drop back down, but not drop back down farther than when it was before. So the correct answer, therefore, is B. Okay, questions 34 through 38. I'll deal with this information here. Number 34 says, how much heat is released or absorbed when 0.05 moles of Cl2 is formed from KCl? So in this case, we can see that half of a mole is used in this reaction, and that releases 437 kilojoules of heat. Okay, so how much heat is released when 0.050 moles of Cl2 is formed from KCl? So now we're talking about the reverse reaction. So first of all, right away, we know for the reverse reaction that delta H is going to equal a positive 437. So when that happens, we know that we have half of a mole that's going to be formed when that occurs. But we don't have half of a mole, we have 0.05 moles. So instead of 437, we can just move that decimal place one spot over to 43.7. And again, because it's in the opposite direction, it's being absorbed, not released. So the correct answer is C. Now, mathematically, how could we show this? We could write 0.050 moles of Cl2, and then we can say for every 1 mole of Cl2, there are, not 1 mole, for every half of a mole of CO2, there's 1 mole of reaction, and then for every 1 mole of reaction, there is 437 kilojoules, in this case positive because it's reverse. So 1/2 is obviously 0.5, so 0.05 over 0.5 is just 0.1, so it's 0.1 times 437 equals 43.7. Okay, number 35. What remains in the reaction vessel after equal masses, not equal numbers of moles, but equal masses of potassium and chlorine have reacted until either one or both of the reactants have been consumed? So we know that KCl is definitely one of them. Okay, so really it's just a question of which one of those two is going to run out first. So when you do a problem like that, sometimes the easiest way to do that is just to make up a fake number. So let's use, for example, the number 40. Let's say we have 40 grams of potassium. Now, where did I get that number from? I just made it up. It doesn't matter. Okay, and then we're going to say the molar mass of potassium is 39 grams per mole for potassium. And then we're going to go 40 grams of Cl2, and the molar mass of Cl2 is roughly 71 grams per mole. Okay, and right away we can see that if we kept going, we could go from moles of K to moles of the product, KCl, which again, the rest of this isn't going to change. Okay, and so we would get a number here that again, 40 over 39 is roughly larger than 1, and Cl2 would be less than 1. Okay, and what that would tell you is that it would tell you that potassium has to be there for the limiting reactant. Okay, and once you know that potassium is the limiting reactant, that means it's going to run out first. So if potassium runs out first, then you're going to have some chlorine left over. So the correct answer has to be C. Question number 36. Which of the values of delta H for a process in the table is or are less than 0? So which of those are exothermic? So here you're going from a solid to a gas. In order to go from a solid to a gas, again, do you absorb heat to do that, or do you have to give off heat to do that? Okay, so solid to a gas, usually you go solid to a liquid and then liquid to a gas, but in this case that is called the process of sublimation, like what dry ice does. Okay, in order to do that, again, anytime you go from a solid to a liquid or a liquid to a gas, or straight from a solid to a gas, that's one, or to go from a gas to a liquid or a liquid to a solid, okay, there's different things that have to happen there. So in this case, to go from a solid to a liquid, okay, you're weakening those intermolecular forces, okay, and then from a liquid to a gas, you're actually breaking them, okay, and that's always an endothermic process. Okay, the reverse is also true. Anytime you go from a gas to a liquid to a solid, or straight from a gas to a solid, okay, that is, you are releasing heat to do that. You got to get rid of heat to go from, think about water to ice. You've got to get rid of heat to do that. Okay, that is an exothermic process. Okay, so this one's positive. Okay, here, what is this process here? You can think about it a couple of different ways. You can think about it as, oh, that's an oxidation process. Or you can think about that as, oh, that's losing an electron. That's ionization energy. Okay, and ionization energy, anytime you lose an electron, it requires energy to do that. So that is a positive value. Okay, here you're going from a Cl2 molecule to 2 chlorine atoms. So you're breaking that bond between the chlorines. Anytime you break bonds, that is an endothermic process. Here, the opposite basically of the potassium one, you're gaining an electron. That's a reduction process. Okay, and that is one that when an electron gets close enough, it releases energy when that happens. So that is a negative delta H. And here you're taking two things that are separate, you're combining them into one, and that is also the opposite of decomposition. That's a synthesis process, which is also exothermic. Anytime you're breaking things apart, that takes energy. Anytime you're putting things together, that's releasing energy. So Y and Z are the exothermic ones. So the correct answer is B. Okay, number 37. It's observed that the reaction producing potassium chloride from its elements goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability of the reaction? So it goes essentially to completion. Okay. Now up here we can see that delta H is a negative value, and you're going from a solid and a gas to just a solid. Okay, so in that case, think about in terms of entropy, that's becoming a much more ordered process. So you're going from a gas to a solid, so that makes delta S a negative value. Okay, but like we saw earlier, delta H is a negative value. Okay, so this is one of those cases where what's driving this reaction towards going to completion has to be the enthalpy part, okay? Because in terms of delta G equals delta H minus T delta S, this is negative, but with a negative delta S, this whole component here is positive. So that makes delta G less thermodynamically favorable. So enthalpy has to be the driving force. So if it essentially goes to completion, we know that the reaction is favorable, so B is out and D is out. But now it's what's driving the reaction. Again, it has to be the enthalpy change only. So the correct answer is A. Okay, and then question number 38, the last one for this section. Which of the following expressions is equivalent to delta H for the reaction represented above? Okay, so we can see that we've got Cl2 plus 2 electrons becoming 2 Cl minuses. Okay, and notice every answer has a combination of X and Y. So X is obviously this equation, Y is this equation. We somehow want to combine those two to make this equation here. So we need Cl2, we need it as a reactant. We have it as a reactant right here. We need 2 electrons. Okay, so that means we have to take this second equation and we're going to double everything, and that means we're going to double Y as well. And then we can just put the two equations together. So it's just going to be X plus 2Y, which is C. Okay, question number 39 is a very easy but very hidden question about effusion. Okay, effusion, remember, is how fast gases travel through the air, kind of like effusion. Sorry, that's diffusion. Diffusion is how fast, like cologne, the smell of cologne spreads out. Effusion is how fast that something escapes out of a tiny hole. So in this case, this is a diffusion process. So what they're looking for is, as these start to diffuse, they're looking for, in what case, where are you going to find one where they meet right smack dab in the middle? Okay, and the number one thing that affects the rate of effusion and diffusion, and here it is, here's that term, diffuse. The number one thing that affects both of those is the molar mass. The smaller the molar mass, the faster they move. The faster they move, the faster they diffuse, and the faster they effuse. So really all we're looking for here is we're looking for an answer where the molar masses are the most similar to each other. Okay, and HCl is about 32, 12 plus 14 is 26, this one's 31. Okay, you go through all the other answers, you find that answer A has the most similar molar masses. Okay, so sometimes that is the key word right there. You're like, what is this question even asking about? But then you see that word diffuse and you think, oh, wait a minute, that has to be what they're talking about. Okay, question number 40. Silicon crystals are semiconductors. Which of the following is a correct reason for the increase in the conductivity of silicon crystals when a small fraction of silicon atoms are replaced with those of a different element? So to make things conduct electricity better, you have to increase the number of valence electrons, okay? And if you look at the periodic table, germanium is below silicon. That doesn't have it. It has more total electrons, but it has the same number of valence electrons. Okay, phosphorus, though, is to the right of silicon. So if it's to the right of silicon, that means that it has more valence electrons, okay? And we don't care about protons. That's positive charges. We care about valence electrons, okay? So the correct answer is A. Okay, number 41. This is one of those questions that take us all the way back to IRV, UVET, and the fact that microwaves do what? They rotate, okay? So infrared produces vibrations, ultraviolet produces electronic transmissions, and microwaves cause rotations to occur. Okay, so it talks about nitrogen molecules absorb ultraviolet light but not visible light. I2 molecules absorb both visible and ultraviolet light. Which of the following statements explain the observations? Again, think about how do I combine those together to get the correct answer. Okay. Visible light does not produce transitions between electronic energy levels, but does produce transitions in the I2 molecule. Okay, so that is our correct response there. Okay, question number 42. Referring to different types of alloys. So different types of alloys. You've got gold. You want to make gold stronger and harder. It's allied with other metals, copper and silver. We're going to look at two different alloys, one of gold and copper and one of gold and silver, each with the same mole fraction of gold. If the AuCu, so the gold-copper alloy, is harder than the silver alloy, what's one of the reasons why that has to happen. So remember that we talked about with alloys, you can have substitutional alloys and you can have interstitial alloys, okay? In this case, notice that copper is a smaller atom than silver or gold is. Okay, so when you displace those, if you think about it, literally think about if you're taking, if you've got a jigsaw puzzle, let's say, and you're trying to put another piece in there. Okay, a smaller piece will always fit into that spot. It may not be the right spot, but at least it will fit into the spot. Okay, notice that gold and silver are roughly the exact same size. So that means it's harder to make the silver one fit in there because it's the exact same size as gold. Whereas because copper is smaller, copper can fit into that space better than a silver one could. Okay, so therefore, and again, that's one of those random ones. If you happen to remember that, great. If you don't, not the end of the world. But that is the correct answer, is C. Okay, question number 43. The photoelectron spectroscopy shown above, remove a 1s electron from a nitrogen atom and from an oxygen atom. So again, in both cases, it's the 1s electrons. Remember, nitrogen has 7 protons. Oxygen has 8 protons. Which of the following statements best accounts for the peak in the upper spectrum being farther to the right? So remember, the farther to the left, the greater the binding energy. So why is the binding energy on oxygen greater than, notice it's around the 550 range, where here you're closer to the 400 range. Why in oxygen is it greater? Because oxygen has more protons, more attraction. Okay, so therefore the correct answer there has to be D. Okay, number 44. Consider those two molecules. You have very, very similar molar masses, but you have a much, much higher boiling point in nonane than you do in trifluoropentane. Okay, nonane, a very, very long nonpolar molecule, has a very, very large surface area, whereas here in 2,3,4 trifluoropentane, you've got, again, those fluorines throw off the symmetry a little bit, but again, nonane has the higher boiling point. If you were to predict it, you'd probably predict this one because this one's probably going to have some stronger dipole-dipole forces. But they're telling you by giving you the boiling points that nonane has to have the stronger intermolecular forces. So why? Again, if their molar masses are the same, the other thing that affects London dispersion forces, which, again, this answer has to be only about London dispersion forces, is surface area, is how long that chain is. The longer the chain is, the bigger the surface area. The bigger the surface area, the stronger the London dispersion forces. So the correct answer is C. Okay, numbers 45 through 47 deal with electrochemistry. So question number 45 asks you, what is the standard potential of galvanic cell Z? So again, galvanic cells means they have to be positive values. So you've only got 2 cell potentials, those 2. So there's one way you can subtract those 2 numbers and still get a positive value that would result in this overall equation here. So you would just take 2.00, subtract 1.22, and you end up with 0.78 volts. So the correct answer is B. Okay, in galvanic cells Y and Z, which of the following takes place in half cell 3? So in half cell 3, you've got iron. So in letter Y, what's happening to the iron? The iron's going from Fe2 plus to Fe. So is that an oxidation process or is that a reduction process? That is a reduction process. Then in Z, you're going from iron with a 0 oxidation number to a +2. So that is an oxidation process. So absolutely, reduction occurs in Y, oxidation occurs in Z. The correct answer is C. Okay, if you replace one of your concentrations with a higher concentration, so now in galvanic cells Y and Z, you've got the iron 2 plus is now 5 molar. So again, remember this is a non-standard cell where we want to compare Q versus the number 1, not versus K. So in galvanic cell Y, iron 2 plus is a reactant. So remember that Q in a galvanic cell Y is going to be the concentration of Al3 plus squared over the concentration of Fe2 plus cubed. And if that number gets bigger, then Q gets smaller. So in that case, Q is less than 1, open mouth to the right. That increases the driving force. So in Y, that would make the reaction, that would make the voltage increase. So the voltage is going to increase in Y. So that means B is out and D is out. Okay, now in Z, hopefully just real quickly, you'll notice that iron is a product. That means the iron's going to go on the top here. That's going to make the Q value go up. That's going to make Q greater than 1, which means that the cell potential, that decreases the driving force. That means the cell potential is going to go down. The correct answer is C. Okay, 48. So in 48, so we've seen this question before in class. So it says the pH of solution of 4 acids. For which of the acids is the value of the acid dissociation constant Ka the smallest? So the smallest Ka means the weakest acid. The weakest acid is the one with the fewest hydrogen ions. And the one with the fewest hydrogen ions is going to have the highest pH. Well, which one throughout the whole process has the highest pH is acid 1. Okay, so the correct answer is A. Okay, which of those acids is hydrochloric acid? Hydrochloric acid is a strong acid. The other 3 must be weak. And again, when the concentrations are all the same, say when they're all 1 molar, which one has the lowest pH is the one that has the most hydrogen ions. And again, since hydrochloric is the only strong acid of the 4, it's going to have the greatest number of hydrogen ions and therefore have the lowest pH. So therefore that is acid 2. And number 50, of the following species, which has the greatest concentration in a 1 molar solution of acid 1 at equilibrium? Again, we don't know what acid 1 is, okay, but whatever it is, let's just call it HA, okay. At equilibrium, you're going to have H plus and you're going to have A minus, and remember, instead of H plus, you can have H3O plus. In every weak acid, when it's just the weak acid, not a buffer solution, not anything else, okay? But anytime you have a weak acid, we know that weak acid, it's mostly all this and very, very little of this. So what has the greatest concentration in that solution has to be that original acid, which means the correct answer is C.